we have three-phase winding here, and these coils are put on top of each other. ID that will say 6.6 kV.
Salam sejahtera untuk kita semua. Selamat pagi Bapak-Bapak. Apa kabar Bapak-Bapak nih? Semoga sehat selalu ya. Selamat datang di acara seminar dengan tema Electric Motor Profile Maintenance. Puji syukur kepada Tuhan Yang Maha Esa atas rahmatnya kita dapat berkumpul di acara seminar pada hari Jumat 5 Mei 2023. Perkenalkan saya Dita dan rekan saya Raya yang akan memandu acara seminar ini hingga selesai.
Baik, saya juga berterima kasih Mr. Paul dan Pak Gemagi dan semua tamu undangan yang sudah hadir di acara kali ini.
Baik, selanjutnya untuk pembacaan countdown akan dilanjutkan rekan saya Raya. Untuk Raya kami persilahkan. Terima kasih.
Ya, terima kasih Dita. Untuk mempersingkat waktu, sebelum acara Megger aku buka, perkenalkan saya akan membacakan susunan acara untuk kali ini. Untuk acara ini saya akan membagi dua sesi. Sesi untuk pertama yaitu presentasi buat testing by Mr. Paul, dan kita ada break untuk lunch dan sholat Jumat ya Pak, yang nanti setelah sholat Jumat acara kita lanjutkan kembali. Untuk sesi yang kedua kita akan mulai setelah sholat Jumat, yaitu presentasi untuk dinamik by Mr. Paul, dan juga ada demo produk, Q&A, atau ada sesi tanya jawab ya Pak ya. Baiklah, untuk mempersingkat waktu saya akan persilakan untuk Mr. Paul. Please, thank you.
You see, these wires and turns are insulated from one another by a very thin layer of varnish. Now I'll pass this round, so you can see. Now this is so you have the conductors here, and then you have like a very thin layer of varnish. Now we could just scratch that very easily, and you would have that. You could potentially have a short. If I was to pull this coil apart now, like that, then we're going to have turns like this. When we push them together, they're on top of one another. Now, if we've got weak insulation between those turns, that's when you get the arcing and the shorting between the turns, which leads to overheating and burnout. And why do we get burnout? Is if you can imagine an electric motor, let's say this little one here, let's say it's a 400 volt supply. Now, when we switch the motor on, the contactors come in, but prior to them actually making contact, which is sprung very fast, just in slow motion, it gets to a point where there's an arc. And that arc on a 400 volt motor is likely to be around about 3,000 volts. So for that arc, we've put in a pulse of energy in that motor, 3,000 volts. So the insulation has to be strong enough to withstand 3,000 volts. Otherwise, you're going to get arcing between the turns. Because if you can get, if I spread that out, if it can skip some of these turns, it's going to go for its fastest path. So by going around all the turns, it means that the insulation is strong to prevent it from skipping. And if it skips, that's a short. And what happens is, during that startup procedure, we also have, if you can imagine your bicycle, you jump on your bicycle, you have to put a lot of energy in to get it moving. Then once it's up and moving, it's a lot easier to get it. Same as electric motor. The current that's drawn on the electric motor is often, if we have a motor that's full load current, is 100 amps. If you can imagine during startup, its actual current just for that time when the motor starts to get going up until it reaches a certain speed is likely to be 7 to 8 times full load current. let's just say it's 100 amps. The starter few seconds is 700-800 amps. You add that to a spike of 3,000 volts on a 400 volt motor because of that arc, and then all that current coming in, it's the worst time of the motor's life. An electric motor's damage is created in the windings during startup procedure. Here we have the type of motor which is known as a servo motor. Now a servo motor is exactly the same once again, has this type of winding inside. However, we have different type of terminations. You can see here and here and here. It's very difficult to test because physically it's difficult to test. But the other difference is on the back of these motors there are what we call resolvers, encoders, tachogenerators that give a signal to the PC to control the motor. So if it wants to change the direction, stop the motor at a certain position, it's all done through the control of the rear of the motor. Now DC motors, as you can see, these are very expensive, to high maintenance because we've got lots of carbon brushes that make contact with the commutator, which give off dust, which is conductive. So if you don't clean the DC motor regularly, it basically wraps the internal elements of the motor in conductive material or dust, just like wrapping it in oil. And then one day, when we start that motor, we lead to flash over, and so DC motors are high maintenance. Every few weeks, we have to take the covers off and clean them out, otherwise they're going to blow up. So now we've got a peak here, peak here, peak here. So we're already starting to analyse, but when we put our hand on the machine, it's just vibrating. We don't know all of this unless we look at the frequency ranges. Now, it's also sensitive enough, so in here we've got our bearing, and if we drew our bearing like that, with balls in, let's say it's got 10 balls, so for every one revolution, we're going to get 10 balls past, let's just say it had some damage here, you're going to get one revolution, 10 of these balls going past that point as we go click, 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 click 10 times before it gets all the way around to one revolution. So we'll get a peak up here at the bearing frequency, which is much higher. But then we can have it on the outside, or we can have damage on the ball itself. So we tend to get slightly different frequencies, but all quite high. And then we get a fundamental electric peak. So all of this type of thing is a typical typical vibration signature. Now if we were to look at that just on its own, it would just be a mess. But as soon as we know the reference, we can start labeling these. So this is imbalance. This is looseness. This is misalignment. This electrical. This mechanical bearing, and so on. And if we had a fan that that it was driving and it had 6 blades, then you'd probably get 6,000. So you can see how vibration works, and that's exactly how we monitor torque, because it doesn't matter. We detect torque through the current and the voltage very accurately, and we can pick up these same frequencies, but we're not measuring them in a vibration format, which is usually velocity, and measured in millimeters per second. We would measure in Newton meters, not millimeters per second. So it's exactly the same, we see the same results, but just slightly different. So as you can see, now there's another measurement that I'm going to refer to as we go through this. There's another graph that we have, and we call it time waveform. Now let's just say that this level here was 1 millimeter per second, there was another one there at 2, another one here at 3. So if you add that together, so we've got 1, 2, 3, 5, 6, 7, 8, 9, we've got an overall reading of 9 millimeters per second. And that's what we call our time waveform. And let's let's just say during as it's in operation, let's just say we had a peak here on this bearing, and we pumped some grease into it, and that disappeared. Suddenly that would drop down to a lower level. So these are our two vibration windows. One is frequency, and the guy that worked for Megger, he invented this for current signature analysis. So we're very proud of it because we held the patent up until just a short time ago. So most of our competitors don't even have this capability. But as you can see, but what I would say, as being a vibration analyst, getting the electric signal from a motor, let's just say a motor that's got two bearings and they're different sizes. So we're going to get a mishmash of two different bearings here. Water is conductive, and we don't want conductive material in electric motor windings because it leads to arcing, shorting, fusing. Especially the water is never clean from humidity, it's always got pollutants in it, and plus dust. Some of the pictures I think you may have seen, even the terminal blocks sometimes, the gasket starts to wear, and you get little suction points. The next thing when you take the motor apart, I've seen it many times, the motor is absolutely caked in dust and conductive material. Any other questions?
For this Megger Explorer 4000,
Yes.
the one that is doing predictive. So can we do this for training data? So maybe we will take a lot of data, a lot of motor, right?
Yeah.
So if we actually want to know if this motor have a little bit changes in time. So we know that. So before we took the data is like this, and after that we can compare the data side by side.
Yes.
Is it possible to do this?
Absolutely, and that's one of the main things. So on every measurement, there is a log, what we call a log screen, and the log screen takes all of the test data and logs it each time, and you've got a graph of plus or minus. I can show you the training. Try this. Sorry, just ignore. So what I'm going to show you now is the actual software. Okay. But the idea of Megger equipment is predictive maintenance, and we understand the importance of condition monitoring, which is looking at the trend of change. As far as we're concerned, the operational status of the application has not changed, then neither should the electric motor insulation levels and everything else. So when we have these units, let's just look at any result. Right? This was a paper built in India. I went to 7 years ago. Lots and lots of motors in here. So just pick a compressor. Bad example. This is a VFD. Now remember those DC pulses, really ugly. So let's look at this one. So let's say, let's look at a parameter of, let's just say current. So if we look at the trend, we only got two results here. But on every result, we've got that window. So current level becomes a trend, and we've got that ability to look at the results over time to see if anything's changing. Because that's basically condition monitoring. We want to monitor the change.
Yeah.
Yes, the answer is yes, just like that. So this is. Any other questions while I've got this software open? It's like I said, across the top here we've got these results. I picked some problems. Oh, this was a power station in New Zealand again. So if I looked at the tool, everything's fine. But when I come here, suddenly I found an issue. Now why would that happen? And the complaint of this particular power station was every now and then the motor would go and vibrate. But as soon as I saw it on the tour, they were looking at whether there was some kind of bearing issue, some kind of some looseness, like back blankets, like bearings coming away. They were thinking it's all mechanical. And they were right. And I knew straight away, but I also knew it was away from the motor, it was the load. And what it turned out to be was there was a valve at the beginning of the pump, and it was a valve that had a pin going through it. The diameter was maybe 2 meters diameter, and the valve opens on that pin. The tests start, they're fully automated, so the test can go from resistance to impedance to insulation resistance to polarization index to to step voltage to high part to surge test to surge PD, and all of those tests can be done just by stood there watching the instrument run, as long as they pass. If there's a fault, then what will happen is it will stop the test and say, hey, are you sure you want to continue? And then you can either say yes or no, or at that point investigate what the issue could be. So this video is doing what I didn't want it to do. I'll also go on to the surge test so that you can see what the surge test is like. Skip through. So, I don't know what he's doing here. Can you all see this, by the way? I'm just interested at the distance. Can you see the colours and the graph itself? I know the numbers down the side you wouldn't be able to see. Can you see it? No? Not really? Okay. So unfortunately doing the demo will be difficult unless you want to gather round. You okay with that? Yeah? Okay. There's plenty of room. If you like to come up, we'll do it physically on the instrument. So we have three-phase winding here, and these coils are put on top of each other. Now often, just for your interest, the coils at the back are wound smaller than the ones at the front. So therefore the resistance is going to be different. So if I measure resistance here across these three phases, the chances are there could be a little bit of difference in resistance, and it's nothing to do with the fault on the motor. It's just to do with the design of the coils and the way it's been physically put into the motor. Now the bigger motors with the thicker coils tend to be more formed, so they do not have that different sizing. So the larger motors, we tend to expect a percentage difference in resistance to be much less, well not much less, a little bit less than what we would expect to see in the smaller winding, where the coils have actually been physically made slightly smaller because they're sitting on top and the circumference is getting smaller. Okay. So what I'm going to do is just come out here. Now, while just a few moments ago, I created an asset. So on this asset here, we've got some motors, and I've got down there, I created Pukul CETM. And all I did was, if I was to select or new asset, and I could call this main drive, pump 6, whatever you wanted to call it. And then once I've done that, I save it. And when I save it, it will come here and whatever it's called, I select it. So full CETM, select that asset. And now any of the tests that we do, so here we have RLC, which is resistance, inductance and capacitance, impedance. And then we have our DC tests, which are our insulation resistance, polarization, step voltage and ground insulation basically. And then we have our surge test and our surge PD. Now, if you notice down the bottom, there's four windows. One is settings, but this is manual, this is automatic, and this is sequence. Now, if I hit manual, basically it means that I just push the button, I turn and I test. But at the end of that, I want to save the test results to something. So I would then have to create a motor, but I've already done that. So I'm not going to do manual, I'm going to go to auto. Now auto, let's just say I come here and I'm going to do RLC, it's going to ask me for what the temperature is at the motor. So if I select it to 22, then it's going to go ahead and do the test. There's a few safety screens, there's one too many in my opinion. And then once we're at the screen of the test, we just hit this button here. And now we're going to go across. It's going to do the inductance and impedance first, because if we did resistance first, because we're putting current through, it would affect these results. The inductance of the circuit will change if it's still got residual current in the circuit. But as you can see, it's fast, it's been done really quickly and easily. And at the end here, we've got our percentage unbalance. And it's the unbalance that's going to tell us whether it's acceptable or not. Now, in the settings, I can change that from 2%, 3%, whatever you feel your acceptability is. In this case, I think we chose 3%, so our maximum is 0.9, 0.5 or 0.5, so it's all thumbs up. So to me, as far as these low-end tests go, there's no issue there, everything appears to be fine. So once I've done that, I'll try to exit. When I try to exit, it says you haven't saved the results yet, so do I want to save them? Yes. Then I'm going to come to the DC tests. The DC test is going to ask me for the temperature again, so I'm going to say 20. I'm going to say 22. What we got here is just what I showed you on the screen. We've got our voltage, our microamp leakage, and our current. Now if I hit start, leave it pushed in for a little while, and then it's going to increase the voltage from 0 up to 500 volts in this case.